All right, for number 2 of 2014, this was a you-do problem, so you should have done this already, and you're going to watch this video to see how you did. In number 2, they just get right to it. It says, let R be the region enclosed by the graph f of x and the horizontal line y equals 4, as shown in the figure above. And in part A, it says, find the volume of the solid generated when R is rotated about the horizontal line. So no like, hey, just find the area between the two curves. It's, nope, we're going to jump right into revolutions here. Anyways, it says that it's revolving around the horizontal line y equals -2. So I'm going to go ahead and first figure out my bounds. So I'm going to figure out where the two functions intersect by setting the two functions equal to each other, setting f of x equal to 4. And then this is a calculator-based problem, so saving this into your y list as y1 would be beneficial, and then saving this as y2 would be beneficial. And then to solve this, you're just going to find the intersections with your grapher. So you end up with x equals 0 and 2.3. So that's kind of nice. It was a nice clean 2.3 for this intersection for x. And then we are revolving around the line y equals -2. Notice y equals -2 is down below the x-axis. Remember, in order to find the volume of a solid when you're rotating, you either have the disk method or the washer method here. And so in this case, you can imagine as this region R is revolved around the axis, you can see that there's going to be a hole, there's going to be a gap inside of it. So therefore this is going to be the washer method. Well, we need a big R, we need our big radius, and our big radius, remember, is the distance from the axis to the upper or the furthest curve. In this case, the furthest curve is the constant. So, and then the little r is the distance from the axis to our curve closest to the axis. So the washer method, remember, said the volume is equal to pi times the integral, in this case from 0 to 2.3, because that was our points of intersection, of big R squared minus little r squared, and in this case dx, because we're revolving it around a horizontal line. That means our cross sections are going to be perpendicular to the x-axis here. All right, anyways, big R, our big radius, how do I figure out the distance from my axis to my curve? Remember, it's always the curve minus the axis, or the axis minus the curve. It just depends on where the curve is. Since the curve is above, we would say 4 minus -2. If the curve was below, we would say -2 minus whatever the curve is. But simplifying this just becomes 6. So the radius of the outer curve is just 6 because that function is a constant. For our little radius, it's going to be our curve minus the axis again, and they named this curve f of x, so we can say f of x minus -2, and that can be simplified to f of x plus 2. Again, I can't use f of x unless it's specifically given in the equation up here, and because this is a calculator-based problem, f of x is okay. We don't have to write this all out, but if it wasn't a calculator problem, you would want to write that all out because you're going to have to solve this analytically, possibly. So now we're going to plug in our two radii into our washer method here. It's going to be v equals pi times the integral from 0 to 2.3 of 6 squared minus f of x plus 2 squared, and then dx. And again, trying to understand this, the pi is a constant. That actually can be distributed to both the r squareds, and the dx can also be distributed in there because we can separate it into two separate integrals if we want. So really what we're doing is we're finding the volume, pi r squared h, we're finding the volume of the outer shape, and then we're subtracting the volume of the inner shape, so pi times r squared h. So remember, we're slicing it into an infinite set of cylinders, and then we're summing up those cylinders, pi r squared h, where h is the width of each cross section. So anyways, that is our equation, and then we're going to just type that into our calculator, being very careful that we type it in correctly, and we get 98.868. If you didn't get this, a common mistake is that you just forgot to multiply by pi, or you typed it in wrong, so be very careful on that. As far as points go, you're going to get 1 point for recognizing that it's a washer method. So if you had pi times the, or sorry, if you had the integral of something squared minus something squared, you're going to get 1 point for the washer method. It has to say something squared minus something squared. If it says something all squared, you're not going to get that point. And then you're going to get 1 point for having the complete correct integrand. So 1 point for this entire integrand expression. You're going to get 1 point for having the correct limits and the correct constant, meaning that you have the pi and then the 0 to 2.3. Again, if the pi's inside or if the pi's distributed in, that's fine as long as it's present. And then you're going to get 1 point for your final answer. All right, for part B, it says the region R is the base of a solid. For this solid, each cross-section perpendicular to the x-axis is an isosceles right triangle with a leg in region R. Find the volume of the solid. So remember that because we're talking about cross-sections, well, the cross-sections that we're talking about are perpendicular to the x-axis, so that means we're going to be drawing vertical lines, and they are bounded by the region R. So that is one cross-section. That red line represents one cross-section in region R, perpendicular to the x-axis. Remember, to find volume of any object that has perpendicular cross-sections, it's just the integral of the area function. We just have to make sure that we are looking at it appropriately. Because we're talking about perpendicular to the x-axis, it's going to be a in respect to x, dx, and our limits are going to be x value. So our limits in this case are going to be 0 and 2.3. The big question is, what is the area of the cross sections? How do I come up with the correct integrand here? Well, that's based on the shape that we're talking about. In this case, we're talking about isosceles right triangles. So there's my isosceles right triangle. And then it says that one of the legs is in region R. So this length is maybe one of the legs, and it's in region R. So this vertical line here represents the length of one of these legs. So how do I express this length? Well, this length is the distance from curve to curve. So it would be the upper curve minus the lower curve. That's how far apart they are. So we would say 4 minus f of x. That is the length of the leg, because that leg is in the region R. Because this is a right isosceles triangle, that means the other leg is the same thing. And then we can figure out the area of a triangle by just saying 1/2 base times height, or 1/2 4 minus f of x times 4 minus f of x. And then that can simplify to 1/2 4 minus f of x squared. A side note here, if it said something like where the isosceles right triangles with the hypotenuse in region R, that means this length, the hypotenuse, would be 4 minus f of x, because that would be in region R. And so that would be a little bit more difficult of a problem, because we'd have to figure out how to create the equation for the area of this triangle if I knew the hypotenuse. We do have examples of that in prior videos and in prior reviews from Unit 8 specifically, so if you need help with that, go back and review those. But anyways, I have my area expression, so now I can just plug that into my integrand here. So we have the integral from 0 to 2.3 of 1/2 times 4 minus f of x squared dx. And then we would just type that into our calculator, and we end up with 3.574. As far as points go, you get 2 points for having the correct integrand, 2 points for having 1/2 4 minus f of x squared, and then 1 point for your final answer. I can't really break down how you would get 1 point on the integrand very easily. I believe if they saw that you understood it was the area of some triangle somehow, they would probably give you 1 point for the integrand, but would have to be written like this in order to get both points. Maybe if you had 1/2 of f of x minus 4 squared, you would get 1 point for that, because technically f of x minus 4 is a negative value, not a positive value. But that's how you grade that one. Let's go on to part C. Part C, it says the vertical line K divides the region R into two regions with equal areas. Write but do not evaluate, but do not solve an equation involving the integral expressions whose solution gives the value K. So we have a vertical line at x equals K that divides R into two regions with equal areas. So if I draw a line First of all, that's going to come in handy. That point of intersection was when x equals 2.3. If I draw a vertical line, I could draw it anywhere. That vertical line is k. Now it says that the two regions that I cut region R into are equal. Now maybe I didn't put it in the right place. Maybe it has to go over to the right a little bit more. I don't know. But it's just a visual here. So how can I write an equation that involves k so that it represents that these two areas are equal? Well, there's a couple ways of doing this. I could write an expression for this area and write an expression for this area, so I'll call that A1 and A2. We need to know that A1 is equal to A2. Well, the region A1 is going to be the integral from 0 to k of 4 minus f of x dx. And again, the area between two curves is always the integral of the upper curve minus the lower curve. So it's 4 minus f of x, and we're only going from 0 to k here. For the other area, that would be the integral from k to 2.3. So the integral from k to 2.3 of 4 minus f of x dx. And we set them equal to each other because that would state that both areas are equal. We cut it into two equal parts. So that's one way of saying that. Another way could have been maybe you looked at the area of the whole thing. Well, the area of the whole thing is the integral from 0 to 2.3 of 4 minus f of x dx. That's the area of the whole thing. Well, what is that equivalent to? That would be equivalent to two of these areas or two of these areas. It doesn't matter which one. So we could say equals 2 times the integral from 0 to k of 4 minus f of x dx. That's another option. Or you could have set it equal to 2 times the integral from k to 2.3 of 4 minus f of x dx. That's another option. There's a lot of different options here. As far as points go, you're going to get 1 point for the area of one of the regions, because at some point you had to divide it. Some point you had to have either this integral expression or this integral expression somewhere in your equation. So you get 1 point for having one of those. You're going to get 1 point for your final equation overall. So whether it looks like this or looks like this or something equivalent to it, that's how you get those 2 points. All right, that wraps up this question. For the next problem, we are going to do a quiz, and that is question number 5 from 2016. It's a non-calculator problem. So go ahead and do it. Set a timer for 12 minutes and see how you did when you come back and watch the next video.